A cylinder with radius 2 centimeters and height 8 centimeters is full of water. A second cylinder of radius 4 and height 8 is empty. If all of the water is poured from the first cylinder into the second cylinder, the depth of the water in the second cylinder will be. Here are our two cylinders. The first one has a radius of 2 and a height of 8, as they state in the question. The second one has a radius of 4, and its height is also 8. And the first one is the one that they fill with water. So all of this is water. And the volume, therefore, if you look at the volume formula for cylinders, is pi r squared, which is the shape of the top. It's a circle, right? If you look at it from a bird's eye view, if you look at it from that view, it'll be a circle. And that's essentially the area of a circle. And you multiply that by the height. So it's a fairly easy formula to remember. And using our numbers, we got pi 2 squared times 8. And that's going to be 4 times 8, so that's 32 pi. And then what they do is they pour all that water into here. So it's going to come up to a certain level. I don't know, maybe up to here, say. And they want you to figure out this height. That height right there. Okay, no problem. Again, exact same. Volume is pi r squared times height. Our volume is 32 pi. And then let's see what else we know. R, the big R, is 4. And then be careful, the h is what we have to figure out, right? The total height of that cylinder is 8, but the volume of the water only goes up to a certain level. So that's why I denoted it small h right there. Okay, this is the equation we have to figure out. So the pi's cancel, and you're just left with 32 is equal to 16h, and therefore h is equal to 2. So number 17, the answer is B. Placed in a pyramid-like stack with each layer completely filled. The base is a rectangle that is 5 oranges wide and 7 oranges long. Each orange above the first layer rests in a pocket formed by 4 oranges in the layer below, as shown. The last layer is a single row of oranges. The total number of oranges in the stack is. All right, well, I'm just going to draw the first layer, which is a 5 by 7. So we've got 1, 2, 3, 4, 5, right, oranges, and then going down we've got 7. So 1, 2, 3, 4, 5, 6, and 7. So this is my orientation. So let's make a little table here and let's discuss this. So initially, this is my orientation, right? This is sort of layer 1, I guess. And in layer 1, the dimensions are 5 times 7, and therefore the number of oranges is 35. Correct? Now, layer 2, how does that work? Well, you put oranges like this. This is how you would place the next layer. Pretty much exactly how they explained it in the question. So when you put oranges like that, now my dimensions become 4 times 6 of that layer. And since it's 4 times 6, the number of oranges is 24. Correct? Layer 3, it would be the same sort of story. I don't want to make this diagram too confusing, so I guess I'll just draw in one more. So the next layer is going to be here. Hope you can see those red circles that I'm drawing. And that's the next layer. And the next layer, if you can see it, it's getting a bit messy, is a 3 by 5. And that's 15. And as you can see, it's going down by 1. So even if you don't want to continue this diagram, you could just continue the table. This will be a 2 by 4, which is 8. The next layer, which is layer 5, is going to be a 1 by 3, and that's 3. And that's it, because they tell you the last layer is a single row of oranges, and that's this row right here, a single row. So now our task is to add up all the oranges, and that's what we have to add up. So 35 plus 24, 59 plus 15, 74 plus 8, 82 plus 3, 85. 85 oranges in that entire stack, and therefore number 15, the answer is D. A cylinder has radius 12 and height 30. The top circular face of the cylinder is the base of a cone, and the center of the bottom circular base of the cylinder is the vertex of the cone. A sphere is placed inside so that it touches the cone, the base of the cylinder, and the side of the cylinder as shown. Which of the following is closest to the radius of the sphere? Let's do some labeling. First, let's draw the radius of that sphere so that it touches the bottom right there. And then the same to touch the side and to touch the tangent point of the cone. And at this point, we have to draw some lines that will help us. The first is from this corner right here to the center of the sphere, and the next one is from the center of the sphere to the vertex of that cone. And now there's a very important property that we must talk about. This line right here is a line that originates from here and goes all the way to the tangent point. This line is the same. It originates from that red dot to the tangent point. And there's a rule that when you have such a situation, those two will be equal. And that's going to be very important. So let's do some labeling now, just concentrating on that. From here to here is the radius of that cylinder, and that they've told me is 12. From there to there is the same as there to there, which is the radius of the sphere. So I'll just call that R, this distance right here. And therefore this distance from there to there must be 12 minus R, from here to here. And as we have established, this distance is the same as that distance, so that is also 12 minus R. 12 minus R. Okay, and we are going to do something very similar, that when you have this point and you draw a line to the sphere, tangent to it, and then you have the same point emanating another line that hits the sphere at a tangent point, those two lines will be equal. So this distance is the same as that distance. Now, this distance right here is 30 minus R, since the top to bottom height is 30 and this is R, same as that. And therefore, this distance must be 30 minus R. So there we go, 30 minus R. So that pretty much completes the labeling of the diagram. And that's pretty much all there is to it. Now, all we have to do is just use Pythagoras. Pythagorean Theorem on this big triangle right here, since it's a right triangle. So that means 30 minus R, or actually the full height, not 30 minus R, 30, top to bottom, squared, plus this, which is 12 squared, is equal to the hypotenuse, which is 30 minus R plus 12 minus R, all squared. So this is 900, this is 144, this is 42 minus 2R all squared. This is 1044, 42 minus 2R all squared. And then you don't need to expand it. Just take the square root of both sides. It'll be a lot quicker. 32.31 approximately is 42 minus 2R. And therefore 2R would be 42 minus 32 minus 31. And when you do that math, you get R is equal to 4.84 approximately. And therefore, number 22, the answer is A. Mike has two containers. One container is a rectangular prism with width 2, length 4, and height 10. The other is a right cylinder with radius 1 and height 10. Both containers sit on a flat surface. Water has been poured into the two containers so that the height of the water in both containers is the same. If the combined volume of the water in the two containers is 80 centimeters cubed, then the height of the water in each container is closest to. Well, the height they're saying is the same. So if this is h from here to here, then this is also h from here to here. Okay. Now they're saying that the combined volume of the two containers is 80. So 80 is equal to the volume here and the volume there. So the volume in the first one is going to be length times width. So that's 2 times 4 times the height. The volume here is a little bit different. It's pi r squared times the height, like that. So this becomes 80 is equal to 8h plus pi r squared. Well, r is 1. That's given in the question, so this becomes 1 squared. So this now becomes 80 is equal to 8h plus pi h. Factor out the h and you get 8 plus pi is equal to 80. Isolate for h and you get 80 over 8 plus pi is equal to h. Get out your calculator. Pi is approximately 3.14, so if you add 8 to it, it becomes 11.14. And now you get out your calculator, and 80 divided by 11.14 is approximately 7.18. And therefore, the one that is closest in the answers is this guy right here, 7.2. So number 23, the answer. A pyramid has a square base with side length 20. A right circular cylinder has a diameter of 10 and a length of 10. The cylinder is lying on its side, completely inside the pyramid. The central axis of the cylinder lies parallel to and directly above a diagonal of the pyramid's base. The midpoint of the central axis lies directly above the center of the square base of the pyramid. The smallest possible height of the pyramid is closest to. The key to figuring out this question is to realize that the smallest possible height of the pyramid is obtained when this part of the cylinder is tangent to one of the sides of the pyramid. And I will draw a triangular relationship to illustrate that. This red triangle I just drew is the illustration that helps understand this question. This point right here is the point where that cylinder is tangent to the pyramid. And that will help you figure out this question. So that is step number 1 of this question. And then what we have to do is draw a diagonal from one corner to the other, like that. And that will also help us figure out some of these lengths. So here we go. Let's talk about this now. The length of the square base is 20. So this is 20 from here to here. And so is the length from there to there. It's a square base. Now, because it's a square, that is going to be a right angle. So we can use the Pythagorean Theorem to figure out the full diagonal right there. So we'll do it over here. Diagonal squared is going to be 20 squared plus 20 squared. And therefore, diagonal squared is 2 times 20 squared. And therefore, diagonal will be 20 root 2. Now, we are told some very important clues actually in the question, that the center of the square and the center of the cylinder coincide. So let's draw a line from this vertice to the center, so approximately here, where this is the center of the square and also the center of that side of the cylinder. Now they told us that the cylinder is having a length of 10. So from here to here is 10. If this line is the center, that means from here to here is half of that 10, which is 5. So this is 5. So I'll just put a 5 there. Now, from here to here is half of that diagonal. Now, the diagonal is 20 root 2, so half of that diagonal is obviously 10 root 2. So from here to here is 10 root 2. Therefore, the distance from here to here is 10 root 2 minus this 5. So I'll just put that here. That is going to be 10 root 2 minus 5. Now, in this triangle that I had originally drawn, I am interested in figuring out the sides of that triangle. And one of those sides is this guy right here. So I will use this finding of 10 root 2 minus 5 to figure out this side. And to do that, I will draw a diagram of the square base if you're looking at it from a bird's eye view. And here we go. We got the diagonal, of course, from one end to the other. And then this line right here that I'm interested in, I've got to draw that in here. Now that line in the diagram extends all the way to the other side, right? Like that. So I've got to do the same kind of thing, but in this diagram that I'm showing in a bird's eye view. So it's going to be something like this. And to make this diagram complete, let's draw the other diagonal. And now let's compare. This guy right there is the same as this right here. All right? And that is very important to recognize. Now, this part is the same as this part. So let's label that from here to here is equivalent to 10 root 2 minus 5. Now, what is very interesting about this diagram is that this is a right angle. And since this was a diagonal, this is 45 degrees. And therefore, this must be 45 degrees. So that means this is the same as that. So since those two sides are the same, this is also 10 root 2 minus 5. So there we go. We just got this side. So I'll just draw it here. That is also equal to 10 root 2 minus 5. Now the next part of the question is looking at this circle right here and this triangle like that. So I'm going to draw this triangle containing this circle, which is tangent. But I'm going to draw it so that you're looking at it head on. Right now it's on a slant and it's very difficult to sort of see. But I'm going to draw it face on. So here we go. And there we go. Exactly like that diagram. The only difference is now I'm looking at it head on. And now I have to draw in my relevant lines. So first from top to bottom like this, touching the bottom. And then from the center of the circle to the tangent point. And I think that should be sufficient. Now let's discuss this. This side right here is the same as this side. So let's label that. We knew that that is 10 root 2 minus 5. This from here to here is just the radius of that small circle. The question told you that the diameter is 10, so therefore the radius is 5. So that's 5 right there. And the other radius is right here. That's also 5, right? Because that's also the radius. Now the other parts of the diagram we don't really know. Like for example, from here to here, I don't know what that length is, so I'll just call it x for now. And then this top to bottom, I'll call that height. But remember, it's not the height of the pyramid. The height of the pyramid is over here. That's that. I'm going to do that later. This is just the height from here to here. So I'll call that small h. So that the height from there to there, I'll just call it small h. And therefore from here to here is h minus 5. Now these are tangent points, so that means these create right angles, right there and right there. And I'll draw one line segment to illustrate some very important point, that if you have a tangent from a point, this point for example, let's call it P, and it goes right here. If you draw a tangent from that same point to the circle, those two lines will be the same. So this distance is the same as this distance. That's very important to recognize. So that means the distance from here to here is also 10 root 2 minus 5. And the good news is this is going to create for us a similar triangle situation. And it will, believe it or not, solve the question. Let's just label it. I'll call this theta, and therefore this angle in here is 90 minus theta. And you'll see, therefore, that this big triangle will be similar to this smaller triangle because they have the same angles. This angle in here is 90 minus theta, and this, of course, is a right angle. So let's figure out the similar triangle relationship. This, which is x, which is the 90 theta side on the small triangle, will be equivalent to the 90 theta side on the big triangle. And on the big triangle, it's the top to bottom, which is just h. And then the other one I'll look at is this side, which is 5 in the smaller triangle. It is the 90 minus theta 90 side. It will be equivalent to the 90 minus theta 90 side on the big triangle, which is 10 root 2 minus 5. So I've got a very good relationship there, my first one. I can come up with another one, and another one involves the following. Same triangles, but different sides. This side, this time, it's the theta and the 90 minus theta side, which gives me h minus 5 in the small triangle. And on the big one, the theta and the 90 minus theta side is that side. So that is actually x plus 10 root 2 minus 5. And then, of course, I'm comparing it. On the small triangle, it's the 90 theta minus 90 side, which is this guy. So that's 5. And on the big triangle, the 90 theta minus 90 side is this side. So that's 10 root 2 minus 5. So there we go. We got two equations, two variables, and now we will use those to solve for h. H is probably going to be the value that's going to help us the most. So here we go. From the first equation, we will get that x is equal to 5h over 10 root 2 minus 5. The 5's cancel, so you're just left with h over 2 root 2 minus 1 for our value for x. And then what we can do is substitute that into here and solve. So instead of x, I'll put h over 2 root 2 minus 1 plus 10 root 2 minus 5 all over 10 root 2 minus 5 is equal to h minus 5 over 5. And let's cross multiply here. If you do, you get 10 root 2 minus 5 just goes over there, and then we can simplify this a little bit. This just becomes 2 root 2 minus 1. And at this point, it's just number crunching because we don't really have a quadratic situation, so we don't have to worry about that. We just have to solve these radicals. Multiply through by this guy, and that will probably help us a little bit. It will get rid of this, and then this just becomes 2 root 2 minus 1 times 10 root 2 minus 5. And on this side, it'll be 2 root 2 minus 1 squared, since I'm multiplying the same thing, h minus 5. And at this point, you can expand, but I think it's easier if you convert it to decimals. As long as you use about 2 or 3 decimal places, you should be able to get the accurate answer. So this becomes a 9.2 1, 4 for that 10 root 2 minus 5. And the 2 root 2 minus 1 is about 1.828. And then on this side, this 2 root 2 minus 1 squared is 3.343. And then, of course, we just have the h minus 5. And then this becomes h plus 16.707. And this is going to become 3.343h minus 16.715. Bring the 16s over, and you get 33.422 approximately. And this is 2.343h. And then divide through, and you'll get the value for h as 14.26. All right, we are just probably a minute away from solving this question. Now we have our value for small h, but we want the value for the big H. So we got our value for small h as 14.26 after all that mathematics. And that small h was this guy right here, top to bottom. But we don't want that. We want the big H. And that big H is represented from the top to the base of the square, which is the base of the pyramid. Now, how do we do that? If I know this, which is h, and I know this, which is 10 root 2 minus 5, how can I figure out this? Well, once again, you use similar triangles. And those similar triangles this time are this triangle and this big triangle. Because of the slant of the diagram, I know it doesn't look perfect, but trust me, those are similar. So that means that this over this is the same as this over this, that relationship. So if I label this big H, that means that big H over this, which is d over 2. Remember, this represents half of the diagonal of the square. That is equivalent to this over that, which is my small h over 10 root 2 minus 5. Now h is what we're interested in. Now d over 2 we calculated earlier, it's just 10 root 2. H we have as 14.26, and then we've got this 10 root 2 minus 5. And now it's just basic mathematics, crunching out some numbers with your calculator. And h is equal to this 14.26. And that 10 root 2 minus 5 is equivalent to approximately 9.142. And if you cross multiply this 10 root 2, that is 14.14 approximately. And if you calculate that, it comes out to approximately 22.05. And of the answer choices, the one that 22.05 is closest to is choice B, 22.1. Has a radius 10 and a height of 30. A spiral staircase, which with constant slope circles once around the outside of the water tower. A vertical ladder of height 5 meters then extends to the top of the tower. Which of the following is closest to the total distance along the staircase and up the ladder to the top of the tower? So they want you to find this distance right here. Now at first you might say, well, how am I supposed to do that? I have no idea. Can't think of any formula. Well, here's the clue. Open it up. Those 3 words, I guess, are the hint. They should have that in the question. Hint, open it up. So let's do that. Let's open it up. All right. So when you do open it up, right, it becomes a rectangle, something like that. Yeah. So what I basically did is just cut it. I cut it, say, down the middle like that, and then I just flatten it out. So the top to bottom distance remains the same. That's still 30. But then this is now the equivalent of the circumference of that circle. Because when you open it up, that's basically what happens. It just flattens out. So this is now circumference. And circumference, as you know, is pi times diameter, or pi d, or pi times 2r. So it's going to be pi times 2 times 10, since 10 is the radius, and that is 20 pi. So 20 pi is basically the distance from here to here. And then now, let's draw that spiral. The 5 meters, which is right here, we'll just draw that right here. That's going to be represented by 5 meters. So I'll draw it in red. So approximately that much, right? So this is my 5 meters. That's this guy right here. But the spiral, when you open it up, it's basically a straight line. And I think that's the key to the question. So it becomes a straight line from that point to the corner. So basically something like this, that. So if you can figure this out, then the rest is easy. And I think that's the challenging part about this question. It's a very good question, though. So what we essentially have boiled this down to is trying to figure out the value of that diagonal plus 5. So really, what we have to do is just find x plus 5. And that's it. Then we'll be done with the question. Well, how do we find x plus 5? Well, just concentrate on finding x, really. And x we can figure out easily with Pythagoras, since that's a rectangle and that's 90 degrees in the corner there. Now, when we create the Pythagorean relationship, just be careful. This side is pretty easy. That's just 20 pi. But this side right here is not 30. This full distance from top to bottom is 30. But we want this from here to here. So that would be actually 30 minus 5, which is 25. So just be careful you don't make that mistake. So now the rest is pretty straightforward. X squared will be 20 pi squared plus 25 squared. And now that's going to be using a calculator with pi equal to 3.14. You'll get 3943.8 approximately. 25 squared is just 625. So adding those two, you get 4568.84, and that's x squared. And then take the square root on your calculator, and you get 67.6 approximately. So remember, our goal is to find x plus 5 because we want the total distance. The total distance along the staircase and up the ladder. So x plus 5 will be 67.6 plus 5, and that is 72.6. And therefore, number 22, the answer is A.